So, in a nutshell, I tried to beat Google's most powerful AI, tried a bit too hard, and now I have 122 math world records to my name. Yeah, perhaps I should explain. So this all started when I first read about Google DeepMind's AlphaEvolve. If you don't know what that is, first, get out from under that rock, and second, it's basically a huge AI coding agent made of an ensemble of AIs which work simultaneously to develop algorithms. So in practice, you give it an algorithm, say one that calculates the longest path to school that doesn't go through the same road twice and never makes a left turn, very useful, and two LLMs, a dumber but faster one and a smarter but slower one, start to churn out thousands of potentially better versions of it. Then they compare the results, and if an AI manages to make the algorithm faster, they stick with its version and run it through the same process. This goes on for many generations until you've optimized the original algorithm as much as possible. And this way, among other things, AlphaEvolve managed to increase the efficiency of Google's data center job scheduling by 0.7%, it improved its own training process, so yes, we technically now have AIs improving themselves, not scary at all, and it found new most optimal solutions to 13 mathematical problems, which were mostly boring and extremely specific, but one of them caught my eye. This one. It found new best ways to fit 11 and 12 regular hexagons into a hexagon of the smallest possible size. This seemed like a fun problem, so I read a bit about it. Apparently, these are called packing problems, and even though there are different categories, they all consist of placing shapes into containers in the most optimal way to achieve something, in this case a container size as small as possible. And it's quite amusing because, while some arrangements look absolutely beautiful, others look like geometry went into a teenager phase. But I thought, hey, if a bunch of stupid AIs with no actual logical reasoning can find a world record solution to this, why can't I? I might get myself on some cool list of nerds. So of course, I decided to give it a shot myself. My plan was to use the best tool out there to solve this kind of problems, and run it on a combination of inner and outer shapes, and number of shapes, which could still be optimized. So I went onto the internet and found nothing. The few programs I actually found were for slightly different problems or for very specific versions like rectangles in rectangles. So if you've watched my channel for a while, you know what's coming. I made my own. Now, I must say, researching this was a pain in the neck due to this lack of existing examples to go off of. However, I did find this. Packing records for the different categories are compiled on Eric's Packing Center. This is a website maintained by Eric Friedman, a mathematician who even has a type of numbers named after him while not being dead, which I think is insanely cool. And if you look up the record holders, you'll find their research papers where they describe the process. Sometimes. So I looked into these papers, as well as reading up on geometrical optimization in general, and devised my plan. And after a while, I found the consensus was that differential evolution did the job pretty well. This is a method where you modify a candidate solution to a problem to improve it according to some metric. In this case, the problem being the packing problem, and the metric being container size. However, this is pretty chaotic, so they usually add a polishing step at the end, for which I went with the CMAES algorithm. Luckily, both of these are available as Python modules, the former part of SciPy, so I made a quick sketch to test, and it seemed to work pretty well. But then I tried it for bigger numbers of shapes, and let's just say it didn't scale too well. Fiddling with the parameters, I realized CMAES was doing basically all the work, so I invited DE to take a permanent vacation and replaced it with basin hopping, which is much more specifically suited to this kind of problem. Like DE, it optimizes for a metric, but it does this through random perturbation of the values, in this case the shape coordinates, meaning that it can be really good at exploration, but also at escaping local minima. I also ended up replacing CMAES with SciPy's minimizer, as it seemed to work better, although which algorithm I chose for it, so L, BFGSB, SLSQP, etc., didn't appear to matter much. So I used these tools to solve for smaller and smaller containers, until the smallest possible container was reached, and I actually got pretty consistent results. As I was pretty sure I had my final architecture down, I started running some tests with more inner shapes to find what the best combination of parameters was. I tried different numbers of basing hopping iterations, different numbers of attempts per container size, and so on, and this didn't scale very well either. I got completely different results each time. They were not neatly packed, which isn't always the case, but it wasn't very reassuring, and the runs were starting to take several straight days to complete. In trying to solve the latter, I learned about compiled Python. Basically, there's this module called Numba, which allows you to partially turn Python from an interpreted language, so one executed in real time, which is much slower, into a compiled one, which is turned into machine code at the beginning and then runs lightning fast, essentially combining the versatility of Python with the speed of C, which actually underlies Python. The first time I ran this, it absolutely took my breath away. Like, stuff that took 200,000 seconds to execute started to take 1,000, although the actual arrangements didn't change. Yeah, I need another overhaul. So, for version 3.0 of my program, don't worry, this is the last one, I decided to take another quite popular approach, a more physical one. Basically, I'd progressively decrease the container size, keeping the shapes as they were, and if they didn't fit, perform some minimization or perturbation until they did. The big advantage here is that I'm not starting from square one at each container size, as I'm keeping the previously accepted arrangement, and we call this warm starting. And wow, did that make a difference! My packings actually started to look solid, so I tried it with 17 triangles in a hexagon, for which the optimal solution was already known, and it matched exactly. And so here is the beautiful final version of my code. I start by setting the parameters, which are specified at runtime, and this is what makes my program so powerful. It works for any combination and number of shapes. The next thing is to initialize the unit shapes and all the dimensions, so I don't have to create them each time, which saves a lot of compute. And then I have some helper functions. This @ngit tag at the beginning is what tells Numba to compile the function and make it so much faster. This first one is to transform, i.e. move, a polygon, given its vertices, while this one is just to rotate its vectors, and you'll see why we need it later. Then, this one calculates a penalty for the inner shapes poking into the container walls. The further they poke, the more they get penalized for trying to cheat. And we do this by taking the dot product between each vertex and the apotheme vector for each container side. This next one calculates the overall penalty by first running the poking penalty function and then using the separating axis theorem, for whose existence I'm very grateful indeed. Basically, if you can find an axis where the projections of two polygons don't overlap, the polygons themselves don't overlap. And given that any gap can be viewed from a perspective parallel to one of the sides, we only need to check the axis normal to the edge vectors. So we project each vertex to each axis, check if the shadows formed overlap, and if they don't for any axis, we know they're not overlapping. Otherwise, we penalize them. Don't you get close to my Sarah! And then this function is the actual execution of our code, which we will run as many times as the number of repetitions is set to, which in my case is 5,000 times. Half of the times, we start with a random arrangement, and the other half, we start with the shapes in a grid. Then, we run the minimizer or penalty function so it achieves the lowest possible penalty with the coordinates and angles as parameters, and if it fails to get below our penalty tolerance of 0.000000001, we run a little basing hopping with the same penalty function to try and get it unstuck. If any of them succeeds, we slightly decrease the container size by a decreasing amount each time so we get more precision for the side length, and keep on until both methods fail. And the reason I made this as a function is that I then plug it into a parallel job scheduler to use all of my CPU cores, each one working off one of the 5,000 of these compression processes we'll be running. Once every attempt is done, we choose the one with the smallest side length and make a plot with its values. So, now that I had this beast of a program, it was time to try and get my name on Eric Friedman's page, which meant trying a bunch of combinations of inner and outer shapes to see if I could optimize any of them. I first asked the man himself about the requirements, and he told me he just needed a picture of the plot and 3 side length decimal places, which my code was perfectly capable of calculating accurately. But now I needed somewhere to run it. I could have done so on my own laptop, but that would have taken up my entire CPU for potentially days, and I needed to work on stuff. So I had to find an alternative. And the first thing I tried was asking for one of my school's computers, explaining exactly what I wanted to achieve. And lo and behold, they told me I couldn't for security reasons. Like, the heck you mean security? Do you consider geometry class insecure as well? So the next thing I tried was to get a VPS. I tried with Oracle, but once again failed to get even the most basic type of instance. Of course. And after going through a bunch of possibilities, they all seemed to require some kind of payment. All of them except Google Cloud. Because it turns out they have a free trial of the paid version in which you get $300 worth of compute for 90 days. It was a one-time thing, but it was worth it, so I enrolled in the trial and got working. The first thing I needed was a way to get the results to reach me, and among all the options, the easiest and coolest one by far was making a Discord webhook which the script instances could connect to publish the results as messages on a Discord server. And it was actually incredibly easy to set up. You just get a link you can copy and send a post request to it. However, I now needed a way to try different combinations of parameters automatically. So I just created shell scripts which would do just this. And now my setup was ready to run. I created a bunch of C40 instances with Ubuntu Minimal in my Google Cloud, as those seem to have the most powerful CPUs, uploaded the Python and shell scripts to them, and watched as their CPU load climbed to 100% and Google's electricity bill climbed with it. I first introduced the brand new categories of triangles in an octagon, squares in an octagon, and octagons in an octagon, as there weren't yet any octagons in the page, and after all, I could solve for whatever shape I wanted. Then, I expanded the existing triangles in a pentagon category, which only had up to 14 triangles, the squares in a pentagon one, which only reached the 15 squares, the triangles in a hexagon one, to which I contributed from 19 onward, and 3 packings, up to 30, for the triangles in a square one. And in the meantime, one of my VM instances was working on my main goal all along, actually breaking an existing record. I made it solve for a few combinations of parameters whose packing my gut told me could be improved, and it actually succeeded. I managed to improve the record packings for 12 triangles in a pentagon, 14 triangles in a pentagon, 20 triangles in a square, and 23 triangles in a square. And just like that, I let my machines use up every last cent of my free trial credit. I then sent Eric my results, and all in all, managed to get my name on the record packings page a total of 122 times. Mission accomplished. And with my goal achieved, it is time to release my tool for the world to use. I have made the program completely open source on my GitHub, which you'll find linked in the description. To use it, simply download the script and run it specifying the number of inner shapes, the number of sides of the inner and container shapes, and optionally the number of attempts, the penalty tolerance, and the final step size. And that about wraps it up. My maths teacher said I should try with 3D next, so I might do that, although I'm also working on my robot, which is giving me a ton of work, but it's turning out great. And before you go, I don't know what YouTube decided to do to my channel, but not even 10% of my subscribers are actually getting to see my videos. I'm getting like 0 views in general, and my subscribers are actually falling. And I use this channel as funding for my projects, so I would really appreciate it if you could like and subscribe if you haven't yet, and maybe leave a comment down below to help me with the YouTube algorithm. Thank you so much, thanks for watching too, and I'll see you in the next video.